Hello, we're going to be running through spring 2019 today, just to get general idea of how to solve all these questions. And we're starting off with Lagrange multiplier question. There are usually one, sometimes two or three of these questions every exam. So it's a very consistent question that they ask, and so knowing how to solve this one is pretty analogous to solving them all. So for our Lagrange multiplier questions, we know that we need fx, fy, and fz. So those are the partial derivatives of our function f, which is the function that we're trying to find the extreme values of. And we know that we also have a constraint, g of x, and we need gx, gy, gz. And we know that all of our gx's, gy's, and gz's are going to be multiplied by some constant lambda that allows us to set fx and, set all of f and all of g equal to each other. So let's find these. These are pretty easy to find. Fx is 3, fy is 2, fc is 6. And then on the other side, I'm going to remove these, our gx is 2x lambda, gy is 2y lambda, and gz is 2z lambda. And so now we can make relations with respect to theta. So theta is going to equal 3 over 2x. Lambda is going to equal 1 over y, and lambda is going to equal 3 over z. And so now we can go in between here, set these thetas equal to each other, and we find that y equals, 3y equals 2x, and we find that z equals 3y. And if we go over here and divide by 2, we see that we have, this is what we're looking for, we have a definition of x and a definition of z, all in terms of y. So now if we go back up here to our constraint, remember once we get these relations, we always want to plug back into our constraint. We can replace our x squared here with 3 over 2y squared. Our y squared stays the same, and our z squared is 3y, so 3y squared, that's still equal to 4. So expanding all this out, we get 9 over 4 y squared plus 9 y squared equals 4. Let's multiply everybody by 4. We get 9y squared plus 4y squared plus 36y squared, and that's equal to 16. Let's add all that up. Add all of our y squareds, we get 49y squared equals 16. Let's divide by 49. Take the square root, and we will get 4 over 7. And now instead of doing all that process over with x and z, we already have these nice clean little relations down here that we can use. So we know that x is going to be 3 over 2 times y, which is, we know, is 4 over 7. And so we find that x is 6 over 7. And then we know that z is 3 times y, and so that's going to be 4 over 7 times 3, which is 12 over 7. And finally, let's go and plug all of these values in for our f of x up here, and we can find our maximums and minimums. And note that I'm only finding the maximum right here. And you really only need to find the maximum if you're dealing with a function, a constraint function that's only made up of squares. Your maximum will be equal and opposite of your minimum. And so if we plug these in, we'll get 3x, which is 18 over 7, plus 2y, which is 8 over 7, plus 6z, which is 72 over 7. And we add all of that up, and we get 14. And since we know that constraint function is made out of squares, we know that our minimum will be equal and opposite, so our answer is B. Okay, moving on to question 2. We're reversing the order of integration of this double integral right here. How they make these work is that you're given an integrand in here that doesn't work with u substitution, and we're putting it into a form where it does work with u substitution. And so really the first thing you should do to start off is make some inequalities so we can graph it. So we know that x squared is less than or equal to y, which is less than or equal to 1. And we know that 0 is less than or equal to x, which is less than or equal to 1. We can graph this thing, and we find that we have our x squared function between 0 and 1. And we got our little box here, and we know that this x squared is less than y, which is less than 1. So we're looking at this area right here. So now let's rearrange our integral in terms of dx dy. We're still going to have the same integrand, so 6 root y cosine of y squared inside there. And in order to pick our new bounds, we're going to draw a line parallel to the x-axis first and see what that line hits first. And it looks like it hits 0 first. So 0. And then if we continue that line, what are we going to hit? Well, we're going to hit we're going to hit this function in terms of x, which will actually be root y, and we can solve for that easily just by finding this y in terms of x, which would be x equals root y. And then for our outside bounds, often they stay the same, but don't assume that they stay the same because some of the time they don't. So for our y, we're just looking for our extreme value, so y actually just runs from 0 to 1, so we can plug that in. And now if we solve, we take this derivative with respect to x. We have no x's in here, so in the end, all that's going to happen is we're going to multiply by y, which is what we want. So we're going to get 6y cosine y squared, and then we're still taking this integral right here. But now you see we've got it in a form that we can use u substitution on it. So we'll set u equal to y squared. du is 3y. Oh, whoops, no, not 3, 2y. And so if we divide out our du, we're going to get 3 cosine y squared, integral 0 to 1 dy. Let's take this in. Well, sorry, I'm doing this the weird way that I do, but we can just finish off our integral by integrating that cosine, and we get 3 sine y squared on 0 to 1. This is just going to be 0. This is going to be 3 sine 1, and we see that is the answer choice. Moving on to question 3, we have a pretty standard polar coordinate integration question, and it's always extremely helpful to graph these. So our integrand, we know that we can replace x's with our cosine thetas and our y's with our sine thetas, but we also know that x squared plus y squared equals r squared. And so we see that our integrand is really 3 root r squared, so it is r, 3r. But we also know that whenever we put something into polar coordinates, we have to add another r in there. So our integrand is really 3r squared, and we'll keep that for later, because we have to take a look at what the region we're integrating in actually looks like. So y is bounded on the bottom by the line y equals x. We can put that in there. And on the top by the hemisphere with radius 1. So that guy is going to run like that, going from -1 to 1. But we know that y is bounded on the bottom by this line that we already drew in, so we know that our region is here. And that's confirmed by our x bounds, which run from 0, here, x equals 0, to the line x equals, well, 1 over root 2 is really root 2 over 2. And we know that the cosine of pi over 4 is root 2 over 2, so that confirms that. So setting our integral back up, we know that our integrand is 3r squared, Let's just stick a drd theta on there. We know that theta is running from pi over 4 to pi over 2, and we know that r is running from 0 to 1. So we take this integral, we're going to get r cubed on 0, 1, and now our integral is just pi over 4, pi over 2, 1 d theta, and we'll solve this, and we'll just get pi over 4. Moving on to question 4, we have a surface area question. Apparently these aren't going to be on our exam, but it's still pretty easy and a good thing to know how to do. So we'll solve it anyway. But really, if you clicked on this expecting for an explanation that matters, you're probably okay. So we know that to find surface area, we have to integrate over the 2D projection of this plane into the xy axis, and our integrand is going to be the square root of fx squared plus fy squared plus 1 dA. This is, I guess, a, however they write it. So if we actually do that, we'll see that fx is 3. So square that, we're going to get 9. Fy is 2. Square that, we're going to get 4. And we got to add our 1 on there. So we have a root 14. And automatically, you get the answer. But we'll actually solve it out just in case. So let's pop a dx dy on the end here. It shouldn't matter which order we choose, and let's solve this thing for x. So, and remember, we're in the projection where z is equal to 0, so this z is really not there. 3x equals 6 minus 2y. X equals 2 minus 2 over 3y. So 2 minus 2 over 3y, that's our upper bound, because this is a plane that's projected above our x-axis, and so we're running from 0, and then for y, we can just solve this guy. 2y equals 6, where x is equal to 0, y equals 3. That's supposed to be 3, but really, y is running from 0 to 3. Okay, we can solve this. We have no x's in here, so in the end, because our lower bound 0, we're just going to end up multiplying by this guy. So root 14, 2 minus 2 over 3y, and then taking this integral with respect to y, we're going to get root 14, 2y minus 2 over 6, which is just 1 over 3y squared on 0 to 3, which is going to be root 14 of 6 minus 1/3 of 9, which is going to be 3. And so root 14 times 3 is our answer. And there we go. Okay, question 5. We're working with the tetrahedron with, looks like they're giving us the origin, an x-intercept, a y-intercept, and a z-intercept as coordinates. So let's just draw this thing even before we look at any of these answer choices. So x, y, z. We have our origin. We have 1, 0. We have 2, 0. And we have 3, 0. And for this question, it doesn't actually, 1, 2, 3. It doesn't really matter if you put the 1, 2, 3 in. It's really just for the visual, because if we go take a look in here, we see that every dx is the same, so we really don't care, and every dy is actually the same too. So all we really have to do is figure out which one of these dz's is correct. We see that this function for x and y are being equal to 0, z is equal to 3. That's why it's our intercept up there. And so we need a plus 3 on the end. So this guy, these 3 are automatically out. And we also see that our slope with respect to x and y is negative in both cases. And so that takes out our last answer choice. And we are done. Okay, question 6, we have a triple integral in cylindrical coordinates to worry about. Well, this is spherical. This is for this question. Not going to worry about that. But we know that our conversion is still exactly the same as polar, where r equals r cosine of theta, and sorry, this is an x. X equals r cosine of theta, and y equals r cosine. Wow. Sine of theta. And we know that x squared plus y squared equals r squared. So we see that our integrand here is 8r squared, but we also have to remember that whenever we're converting a rectangular or Cartesian integral into cylindrical or polar, we have to multiply by r. So we're actually going to have an r cubed in there. And immediately we can go to our answer choices and take out everything that doesn't have an r. Sorry, that doesn't have an r cubed. And if we're being really specific, we actually already know the answer, because this guy, it has our r cubed, but it also has a z. We have no z. We never have any situation where we add a z in there. So we actually already have our answer. But let's just confirm by converting everything else. So if we convert this integral here, we remember that z always remains the same. So this is still with respect to z, which is confirmed up there, and this is going to be 0. And we remember that we got this relation here, so this top bound is going to be r. And then for our y, this function right here is just the hemisphere with radius 3, so -3, 3, 3. And so we can see that and say, okay, dr, r runs from 0 to 3, and then since x is running from -3 to 3 up here, we know that theta is running from 0 to pi to meet that requirement. And we see that that's exactly what we've got over here. But it's these little things, like if you didn't see that z, or if you computed these three guys, it would be pretty easy to just choose B by accident without noticing that little z that they kind of snuck in there. Okay, question 7, we have a spherical integral to worry about, and got our little conversions right here, which is a little useful. And this is an interesting one, because seeing this x squared plus y squared, you'd immediately think that it's a cylindrical integral, but this one is not. So we see that we're solid region in the first octant, outside of one sphere and inside another sphere. So if we set up the basic form of our integral, d rho d phi d theta sine phi rho squared. So we know that those are in there before we stick anything else in. Let's see what our rho runs from. Well, we know that x squared plus y squared plus z squared is a rho. So rho, we're in between these two guys. And so rho is going to run from 1 to 2, because we have to take our square root. So rho from 1 to 2. Phi, well, we're in the first octant. In this little area here, so phi has to run down from the z-axis to the xy plane, which is pi over 2, 90-degree angle, and our theta also can only run a 90-degree angle, so we get pi over 2. But let's go take a look at our integrand. We have to change this x squared plus y squared into spherical coordinates. So let's replace our x squared with p, sorry, I call it p in my head, it's really rho, p rho squared sine squared phi cosine squared theta, and then our y squared will turn into rho squared sine squared phi sine squared theta. And what we can do here is factor these two identical parts out, and we'll get rho squared sine squared phi is cosine squared theta plus sine squared theta, so 1. And we know that we have to multiply this guy by what we already have in our integrand, and so we're really going to get sine cubed phi p to the 4. So if we evaluate this, we're just going to ignore this. We'll add him back later, but if we take our integral with respect to rho, we're going to get rho to the 5th over 5, evaluated on 1 to 2, which is going to be 32 over 5 and 1 over 5, so 31 over 5. And then we'll add our sine cubed phi back in and take our integral from 0 to pi over 2 d phi. We can do some u sub here, so we're going to get 31 over 5 integral from 0 to pi over 2 of sine of phi 1 minus cosine squared of, that's a phi, there we go. And we can set u equal to cosine of phi and du to negative sine phi d phi. And let's see, we'll replace our bounds. Cosine of 0 is 1, cosine of pi over 2 is 0. We're dividing out a negative sine phi d phi. So this integral is going to turn into u squared minus 1 du. And remember that we still have this 31 over 5 outside. So let's take this integral. We're going to get u to the 3 over 3 minus u on 0, 1. This is just 0. This is 1/3 minus 1. So negative 2/3, but since it's down here, we're subtracting it overall, so we're going to get 2/3. So 31 over 5 times 2/3. And since we're not dependent on theta at all, this pi over 2 is just going to get multiplied in, so pi over 2. And we find that these 2's cancel. We're going to get 31 pi over 15. And we are done. Okay, question 8. They throw these weird little gradient algebra questions in here that really aren't that bad at all. It seems more like exam 1 material, but let's go. So let's see. We're given a function x. We're given a function g. We're not given any of their gradients. So let's just go take them all, because we see that we need both eventually. So fx is going to be 2x. Fy is going to be 3y squared, and fz is going to be 4z cubed. Let's see, gx is going to be 3, gy is going to be 4, gz is going to be z. Okay, and we see that we're looking at the gradient at 2, 1, negative 1. So this guy's going to be 4, this guy's going to be 3, and this guy's going to be negative 4. I'll write that out a little better. And we see that we want this gradient to be perpendicular to g at some value a, b, c. Well, our a and b are already defined, and so are these three. So we only have one unknown. They're making it really easy on us. And we know that in order for them to be perpendicular, their dot product has to be 0, since they're both gradient vectors. So we're going to get 4 times 3 plus 4 times 3 plus negative 4 times z. And we'll get 24 minus 4z equals 0. 4z equals 24. Z equals 6. And they're calling this z value c. So we'll play by their rules. And our answer is c. Okay, question 9. We've got a line integral. And it's a, let's see, it's a line integral in this form. I don't really have a name for these, but you'll get ones with multiple dy's, dx's. But we're also on a line segment, so we need to make a parametrization for that, and that's no problem. We'll establish that t runs from 0 to 1, because you can always make it so t runs from 0 to 1, and it's often the easiest way to do it. So we see that x starts at 0, so x is going to be 0 plus 2t, because when t is 1, we want x to be 2. And y also starts at 0, and we're going to add a 6t on there. We might as well go and find dx also, which is just 2, and dy, which is 6. So now we can just plug everything in. We're going to have integral from 0 to 1 of xy, which is just going to be 12t squared, dx, which is just going to be 2, plus, minus y squared dy. Well, y is 6t, so that's going to be 36t squared. Dy is just 6, so times 6, and we're going to slap a dt on there. So this is the integral from 0 to 1 of 24t squared minus 216t squared dt. And, you know, I'm not going to embarrass myself and mess up this basic subtraction and division, but you end up with negative 64. I believe you get 194t cubed over 3, where t is equal to 1, and, well, sorry, negative, which is negative 64. Okay, moving on to another line integral. This exam has 2 of them. That's a pretty normal amount to expect. We see that we have the integral from 1 to 2 of 9x. We can just go plug these guys in. We don't really have to wait for anything. 9x, so 3t cubed. That's not a very good 3, is it? 3t cubed over y, which is t4 over 4. We can rearrange this guy, dt. We can rearrange this guy to the integral from 1 to 2 of 12 over t. This is really still a ds, because we need to multiply by the square root of the squares of the derivatives, so x prime squared plus y prime squared. And so we can set that up. Dx is going to be t squared, dy is going to be t cubed. We square those, we get t to the 4 plus t to the 6 ds. And this still looks like a terrible integral until you pull out a t squared. So this guy is really equal to the square root of t to the 4, 1 plus t squared. And we know that we can just take this guy out as a t squared. So really, our integral is the integral from 1 to 2 of 12t root 1 plus t squared dt. And we can do u sub, but we can actually just, you know, do it in our heads a little faster. We're going to get 12 over the 2 that we divide out from here times 2/3 1 plus t squared to the 3 halves on 1 to 2. And, you know, we'll find that this is, all simplifies down to 4. And if we go over to our answer choices, that only leaves us one option. Let's just confirm that we did everything else right, though. We're going to get 4, 1 plus t squared to the 3 over 2. Well, if we plug 2 in for t, we're going to get 4, 5 to the 3 halves. And if we plug in 1, we're going to get 4, 2 to the 3 halves. And we see that that is indeed equal to 4, 5 to the 3 halves minus 2 to the 3 halves. And that's that exam. I hope this was vaguely helpful.